My name is Manabu Sugimoto. Maybe in Chinese pronunciation, my name should be Shangben, and I'm from Kumamoto University. Shangben Dashi. Hello, China, and Chinese people, and hello, researchers from all over the world. And I'm very happy to give a talk today. And before going further, let me appreciate the great organization of this symposium. Thank you very much, Pablo and Izao. This is a very wonderful meeting, and to Izao, I really appreciate your kind invitation to this symposium. I still remember the wonderful days we shared in the University of Illinois at Professor Nancy Macris' laboratory. Okay, my talk is about electronic structure in numerics. I'm suggesting dysentery. Okay, let me start by discussing about a tiny issue that is about skin whitener. Are you interested in this? This topic was introduced by one of my female students. She is very interested in cosmetics, and when she came into, she joined my laboratory, she asked me that, "Oh, professor, how can I design the cosmetics just like a skin whitener?" And at that time, I was a pure computational chemist, quantum chemist. That's why I was quite, struggled. I was very confused about her question, and I tried to do, I thought that I should do something for her. And then I found that machine learning technology would be useful to cope with such problem. As you might know, the skin whitener is the chemical that inhibits the activity of tyrosinase. Tyrosinase works as an enzyme for melanin synthesis, and this is a tyrosinase. And strictly speaking, more precisely, we should say that the monophenol monooxygenase plays a role to synthesize the melanin. Melanin is synthesized biologically in our body from tyrosine, and it is oxidized into dopaquinone, dopachrome, and finally it goes to the melanin dyes. And then the mechanism of tyrosine oxidation is well known. The copper-2 dinuclear copper center is responsible for the oxidation of phenol derivatives, including tyrosine. And such mechanistic analysis has been done experimentally and theoretically by many groups. It is well known, but the question is, once we are given a list of compounds that inhibits the tyrosinase enzymatic activity, how can we predict which molecule is strongly reactive, most effective, and how can we make it by using quantum chemistry? In such a case, our fundamental question is, do we try to perform quantum mechanical calculations for all the molecules listed in this table? Of course, I know the Chinese people are quite aggressive and hardworking, so they maybe one of the Chinese young researchers will try to do quantum chemical investigation for all the molecules listed here. But what happens to in the next case? The next case is the use of molecular database. When I use the knapsack database, that is a natural product database developed by Shigehiko Kanaya. He is working in Nara Advanced Institute of Science and Technology. When I use his database, I can pick up what kind of plants, flowers includes the ingredients potentially active for melanin inhibition. When I checked his database by inputting the query here, I'm sorry, this is a Japanese word, and then I was suggested to focus on 3 types of plants like this, and by checking the chemicals included in these plants, I found 57 compounds are listed in his database, and one of them should be responsible for the melanin inhibition to prevent melanin synthesis. And our question now is, we must find which component, which chemical is important as a skin whitener. So in such a case, how do you do? I mean, do you try quantum chemistry calculations for all the compounds? Some of them may be skin whitener, inhibitor for the tyrosinase, but most of them would not be an inhibitor. It doesn't work at all. So even in such a case, do you try quantum chemistry calculations? So in order to cope with such a problem, I'm now thinking that we should apply AI technology, machine learning, and computer simulations also. So such a combination of these modern computational technology should be a key to fix this problem, to find the problem. But the question at this stage is, what level of information do we need? Do we need atomistic information? Maybe it's true, but the structural information will be fine, be satisfactory. And I'm originally a quantum chemist. That's why my answer is very simple. Why don't we go into the quantum chemical studies? Of course, we should not do the overall reaction pathway analysis by using quantum chemistry calculations. So that we need to develop some sort of techniques that will reduce research time. It should shorten the research investigation time. So recently I'm suggesting electronic structure informatics that uses the descriptors describing important electronic features of molecules. Of course, in order to get features of electronic structures, we should use the quantum chemistry calculations. Of course, if we are lucky, we can use some experimental data, because experiment also obtains the information about the electronic structure. But as a quantum chemist, I can use a variety of software. That's why I'm suggesting to use the quantum chemistry softwares in order to evaluate electronic structure informatics descriptors we are suggesting. And at this stage, I'm focusing only on the electronic structure, but it does not mean that we can forget about the properties related to vibrational modes, because normally we are working, quantum chemistry is based on a crude Bohr-Oppenheimer approximation, crude adiabatic approximation, and the final goal is to obtain the exact non-adiabatic wave function. And so in many cases, we apply to a kind of, say, perturbation-like approach to introduce some corrections to augment the information required to understand the chemical phenomena. For example, if we use the very convenient solid-state physics expression of the model Hamiltonian in this way, we know that the Hamiltonian should contain the term including transfer integral that corresponds to the resonance integral in the Hückel approximation and on-site Coulomb repulsion. And in addition to these terms, we should focus on a vibrational mode coupled with the number of electrons. So this term may be understood as a term representing the electron phonon or electron vibration coupling. So in addition to the pure electronic structure information, we should mind about the coupling between the vibrational modes. Anyway, by including such information, we may focus on solving the Schrödinger equation. And in this case, we have two purposes. Before discussing about this issue, I'd like to introduce the usefulness of such kind of mathematical modeling in order to understand the chemical phenomena, just like a catalytic reaction and whole transport in organic materials and the light emission properties. A long time ago, many years ago, I worked on computational quantum chemical study on the whole transport materials for organic light emitting devices. And I also did some work on say, emission properties of the LQ3, that is a prototype compounds in OLED. And I also worked with I also worked on a mechanistic analysis of a catalytic reaction like this. And in all the cases, I was successful to apply the model Hamiltonian approach for the analysis after quantum chemistry calculations. That's why I'm thinking that I think that this type of, say, model Hamiltonian approach would be very useful to understand, predict the chemical phenomena. And so far, I have been working on various issues in chemistry as an applied quantum chemist. And through those experiences, I think that the combined use of computation and theory and machine learning will be very useful. And next, I'd like to explain my standpoint, my focus in the process of compound screening. This will be a very this type of slide may be very familiar to you, but let me explain. First, experimentalists want some promising compounds, and then they come to a computational chemistry laboratory to do computational analysis or make predictions. And then we do quantum chemistry computations on functional molecules suggested by experimentalists. And then we do detailed analysis after calculation, and we try to find important data. And then we try to understand the chemical phenomena. And on the basis of this understanding, we try to discover construct the design principle, and then we will do chemical design of molecules. But this is, of course, this is quite a rational approach and reasonable to do, but this is quite time consuming. And sometimes we don't need to understand completely. If we are lucky to know the structure property relationship, we can go further. By using this relationship, we can do the computational in silico or virtual screening on computers. Then we can suggest new compounds to the experimentalists. So my point is that the field under this dashed line is the road, the field computational chemistry can work, and most of the quantum computational chemists are working on how to compute the electronic structure or vibrational state efficiently by using computers. But in my focus, I think I should try to develop a method to do the latter part of this theoretical research. And I'm quite interested in this area circled in dashed yellow line. Okay, let's think about to derive the quantitative structure property relationship. In the biology field of pharmaceutical sciences, the property should be replaced with the activity. Now, we'd like to have a mathematical equation describe the molecular property just like this. And in this case, the input would be the R. R is the structure of molecules, atomic configuration of molecules. And if we can establish this relationship, we can do exhaustive virtual screening by generating virtual hypothetical molecules on computers. And of course, in that stage, we should have the machine learned function F by doing the supervised machine learning. And this type of equation can be derivable from in three approaches. One is accidental or intuitive discovery after a lot of quantum chemistry calculations. And this is the first approach. But the second smart and a clever approach would be to use the physical mathematical modeling. And then you may be able to mathematically relate property with the structures or some sort of other elementary molecular properties. And in my approach, I'm using the machine learning strategy. And when we focus on the activity relationship, the famous approach for QSA, quantitative structure activity relationship, was established by Professor Hansch and Toshio Fujita. He is Japanese, and they suggested very wonderful element and practical useful method. They suggested to use the molecular properties, physical organic chemistry properties, just like a Hammett sigma or log P. P is a partition function of molecules into water phase and octanol phase. And they try to derive the math equation to describe the activity on the by using the physical chemical properties of molecules, like these properties, log P and Hammett sigma or something like that, and if pi parameter. And these approaches, when I summarize these two approaches, the QSPR suggests that the molecular structure should be related to the property, and the Hansch-Fujita approach suggests that the activity, that can be property, should be described by the fundamental property derivable from physical organic chemistry. Here I like, but from the viewpoint of quantum chemists, we are thinking that the wave function is a very fundamental mathematical function. It should be a descriptor. Therefore, we like to establish such equation to describe activity if we are interested in a drug design. But this is not easy. Of course, as you know, the wave function is a pivot of the information to make connections between molecular structure and molecular property, because all of them can be described by the wave function. But the question is, why is psi is useful or not for machine learning? At present, I'm not optimistic about this, but we should try this approach, because Professor Rod Hochman suggests that the isotope analogy would be a good concept to pick up the design a new molecules, functional molecules. He says that if two molecular fragments have the same Lobel structure, Lobel feature, then these two compounds should show the very similar chemical reactivity. Therefore, he suggests that the wave function analogy should be pursued in order to replace one compound with another. So this is a very fascinating approach, but at present, I have no idea to go forward. Therefore, I'm focusing on a different aspect in quantum chemistry-based machine learning. That is quite simple. If we focus on, say, inhibitory equilibrium constant for inhibitory activity of a drug molecule against enzyme, Ki, this quantity is very famous, important quantity to describe how strong the inhibitor molecule works. And this is related to inhibitory concentration at 50%, IC50 parameter. This is very frequently observed in pharmaceutical sciences, and these parameters are related with each other. And as you know, the equilibrium constant can be related to free energy changes. Therefore, the energy descriptors should be employed in order to predict, in order to derive a machine-learned function for the IC50. So my point is to focus on the energy. It seems reasonable because psi and E are mutually related. And so my activity so far is on the basis of energy. So that we are doing energy-based electronic structure informatics. And as an ESI descriptor, I'm suggesting 4 types of descriptors. One is those describing the energy changes related to chemical reactions. And the second type of descriptors is about those describing molecular response properties, because properties appear as a response to the external perturbations. That's why we should focus on the electronic energy responses against external stimuli. Third type of ESI descriptor is about the molecular recognition. This includes the size of molecules, geometric anisotropy of the molecules should be included, in order to take into account the molecular docking. Also, at the same time, we are including the factor describing the phase transfer because our biological system is heterogeneous. I mean, we need to focus on the aqueous solution and the protein phase that is, say, organic phase that is completely different from the aqueous phase. Therefore, when we think about the, say, binding of the ligand into the binding pocket of the protein, we need to mind about the, say, desolvation of the solute. Therefore, we are taking into account the electronic descriptor describing the phase factor. Okay, let me discuss about the first issue. And first descriptor, and this is an potential energy surface describing a chemical reaction. And if we are allowed to describe this type of curves by using parabola, just like this, we know that the activation energy can be described by the driving force of the reaction, as well as the reorganization energy described as lambda. And this is a very simple Marcus equation, the formula included in the Marcus expression for the electron transfer. Therefore, for us, the fundamental quantity is delta G0 and lambda. And we may be able to calculate a component of these energy factors. For example, if you focus on a redox reaction by cyclone P450, we need to mind about the ionization and electron attachment in the process. Therefore, we should mind about ionized state and electron attached state in addition to the spin singlet neutral ground state. Speaking about the molecular response properties, we know that the response properties are described by using the second order perturbation theory. It means that the properties should be described by using the excited state information, excitation energy, and the transition energies, transition matrix element. And this is a copy of my first work under the supervision of Professor Hiroshi Nakatsuji. And in this study, through this study, I learned that the excited state should be taken into account to describe the molecules. When we focus on the van der Waals interaction and described by the Lennard-Jones potential, it can be derived on the basis of second order perturbation theory. Therefore, in order to describe the intermolecular interaction, we should mind about the energy information on the excitation energy as well as the transition dipole moment. So what we are doing in our informatics approach is to do electronic structure calculations on ground state molecules, and we calculate excited states by using the TDDFT. We also obtain the vibrational information through normal mode analysis using quantum chemistry packages. And for the spectroscopic properties, we calculate the similarity of between molecules with respect to reference molecule. That can be a relative distance between the reference molecule. And so we are using the shape topological structural properties by using the volume option in the Gaussian, and also we are using Mathematica to obtain the box size described just like this. The phase transfer can be describable by using the solvation energy or desolvation energy. And in our approach, we are using very simple PCM model in order to evaluate the solvation energy. So finally, we are suggesting only 21 descriptors, and we are trying to use these descriptors for a variety of say chemical phenomena, just like a toxicity of molecules, inhibitory activity of drug molecules, and whole transport properties, whole mobility analysis, like that. And I have almost running out of time, so let me go first. So this is the first example of application. This is about the YY plot for the inhibitor molecules for fatty acid synthase enzyme. I and we applied a random forest to make predictions of the IC50 for these compounds, and the correlation between the experiment and the predicted value was very good. And when we slightly extend our descriptor set by including the hydrogen bond energies, we could reproduce the ligand receptor docking energy evaluated by the fragment molecular orbital method. And there is, in Japan, we have a fragment molecular orbital energy orbital calculation database. And in this database, we have a binding energy. Therefore, we did the supervised machine learning using random forest with our own descriptor. And this is a correlation between prediction of ourselves and data listed in this FMODB. And the correlations are very good. And speaking about the application to the antimicrobial agent, the agreement is just like, was also good. And by using this machine learning approach, we investigated potential candidates for the antimicrobial compounds from the natural product database. And we listed top 20 compounds, which are potential candidate for the effective antimicrobial molecules. And we checked it conceptually by referring to the PubChem database. And this, I hope that this approach would be very nice for the scaffold hopping in pharmaceutical sciences. And this is a final application. I have more applications, but this, because of time limitation, this is the last topic I am introducing. This is about the toxicity prediction of the phenol compounds. We evaluated electronic structure descriptors for 25 and 250 phenol derivatives, and we predicted the toxicity activity of these molecules, and this is a result. And we also did some classification work. Experimenters suggest the classification of mode of toxic action. And by referring to the experimental classification, we did XGBoost classification together with a Sugimoto algorithm. This is the algorithm for the imbalanced database.
Sorry, Professor Sugimoto, can you finish in 1 minute?
Okay,
sorry.
Okay, so it was successful. I have more applications, and I'm also enjoying a variety of molecular dynamics simulations, but let me finally conclude my talk. Okay, what I have done is to think about a variety of computational method and theory, and I have just suggested electronic structure informatics on the basis of theory, computer simulation, and data science. And 21 descriptors were suggested, and I'm thinking, I think that this descriptor set would be useful to derive machine learning models. And I also introduced some applications in my presentation. And now we have just done electron energy-based ESI, but we should go forward for the wave function-based ESI. Thank you very much for your kind attention, and I'm happy to have some questions.